In this video lecture, we're going to cover Chapter 17, Section 5, Solubility Products. So here we're looking at a chemical reaction, an equilibrium reaction, where we have barium sulfate solid in equilibrium with its aqueous ions. So again, these should be real equilibrium arrows. And the cation is barium 2 plus, anion is sulfate 2 minus. So in Chem 101 and Chem 60, we just talk about the fact that if this compound is insoluble, you know it's insoluble because barium and sulfate do not dissolve in water based on our solubility rules that are in the front of the study guide. So we just, in Chem 60, Chem 101, say the compound's insoluble, that's that. Well, in Chem 102, in this chapter, when we're looking at complex equilibria, we're going to see that, yes, most of the compound is solid, but there is a small amount of ions that are actually dissolved in water. And that kind of makes sense. If you have barium sulfate solid in water, there's going to be a few of each of these ions that will indeed be aqueous. So that's what we're going to cover in this section. Looking at this, our KSP expression then for this reaction, remember products over reactants. So we would be looking at barium 2 plus times sulfate. And we don't have a solid included in here, right? So that'd just be over 1. Remember, for our K expression, products over reactants raised to the stoichiometric coefficients, and you only include aqueous and gas. Solid, liquid, you ignore, because its concentration doesn't change because it's a pure substance. One important thing to note is something called a molar solubility. Write the definition up here. Molar solubility. It's the solubility of a compound, and the units are moles per liter, which remember is the same as molarity. So we'll be talking about molar solubility of a compound, and that just tells you how much is actually dissolved in water. What we're going to see, we can calculate molar solubility of a compound directly from a KSP value. So again, this is a KSP specifically for a solubility product, constant. So for practice exercise 8, we're given the KSP of LaF3, 2 times 10 to the negative 19th. Realize negative 19 exponent, that's a really small number. K is really, really small. That means we have very few products and mostly reactants. We're going to see that's always the case for KSP, which makes sense because we're looking at compounds that are insoluble in water, so the K values are going to be really, really small. You have mostly reactants, which is the solid. The question is, what is the solubility of LaF3 in water in moles per liter? So again, the solubility in moles per liter, that's called our molar solubility, is what we're trying to find. Okay, so the very first thing you should do anytime you have a KSP problem is write the reaction. It's important to know for our KSP reactions, you always start with the solid as the reactant and the products are the aqueous ions. So for LaF3, that will be our solid because we're given a KSP value for it. In equilibrium with the cation, so I know that I have 3 fluoride, right? Fluoride's a monatomic anion. We know that from the periodic table. That means La is a 3 plus ion. And the KSP expression is an La3 plus F minus cubed. And to solve for our molar solubility, what I need to figure out is what is the molarity of either the La3 plus in solution or the F minus in solution, because I can use a mole ratio to solve for the molarity of the LaF3 that's actually dissolved. So to do that, we can use an ICEQ box with molarity. I know it's ICEQ with molarity because I'm looking at equilibrium arrows. Solids we don't include. We're assuming we start with no products, so just the solid. So how we're setting up this problem, we're assuming we have the LaF3 solid, we then add water, we stir, and we want to see what is the concentration of the ions that do indeed dissolve. So that's why we start with 0 for the products. The change, same as before, plus x plus 3x. And what this is saying is that over time, you're going to form this 1 to 3 mole ratio of La3 plus and F minus in solution as your solid product starts to dissolve. And then at equilibrium, once that has been reached, we have, again, this x to 3x relationship. So the main reason for this ice box is just to show this 1 to 3 mole ratio. We're using our same steps with our ICEQ ice box, so ICEQ with molarity. We don't need to use molarity with the solid, obviously, but our x will give us answers in molarity. And now we have to think, how do I solve for x? We have the numerical value of k, so we can solve for x. So KSP is 2 times 10 to the negative 19th. And now instead of La3 plus, I'm going to put this x value. Instead of F minus, I'm going to put 3x. And we can't forget the cubed. And now with algebra, we can solve. So I know that 2 times 10 to the negative 19th equals x. 3 cubed, remember, is 27. X cubed. 2 times 10 to the negative 19th equals x times 27. X cubed is 27x to the 4th. Now using our rules of algebra, I can solve for x. X is going to be 2 times 10 to the negative 19th divided by 27, and then to the 1/4 exponent. So on your calculator, this is going to be important to know how to do. I'm going to type in 2e negative 19 divided by 27, then exponent, caret, to the parentheses 1/4, close parentheses, enter. And I got 9.28 times 10 to the negative 6th. And this would be units of molarity, moles per liter. So make sure you can get that on your calculator. If not, ask for help in office hours. And this is our x value, right, which stands for La3 plus. But what I want is the molarity of the entire ionic compound. So using our mole ratio, I know that 1 mole of La3 plus contains, or is in every 1 mole of LaF3. So that also equals, with sig figs, 9 times 10 to the negative 6th molarity LaF3 dissolved in solution. So this makes sense. It's a really small number because the compound is, in general, not soluble, but a very small amount of the ions will dissolve. And so this would be called the molar solubility of LaF3, which we calculated based on the LaF3 solid equation and the given KSP value. Another factor affecting solubility is a common ion effect. So this again is our equation for barium sulfate. So this would be we're getting our KSP reaction for barium sulfate, which is insoluble in water, dissolving into the ions. Again, we're focusing on the very small amount of the ions that will indeed be aqueous. And I know based on Le Chatelier's principle, if I add any products, equilibrium shifts left, making the compound less soluble. So this is again called the common ion effect. So if I add something that has sulfate to a container of barium sulfate solid in water, adding more sulfate shifts the equilibrium to the left, making the compound less soluble. So shifting left makes BaSO4 solid precipitate more. Or precipitate more out of solution. So we're going to see how does the common ion effect affect solubility. And we'll look at that on the next slide. So in this practice exercise 9, we're looking at magnesium 2 hydroxide. So we're told the value for KSP of manganese 2 hydroxide is 1.6 times 10 to the negative 13. Calculate the molar solubility of MnOH2 in pure water and also in a solution that contains 0.020 molar NaOH. So in pure water, A, that will be exactly like what we did in LaF3. And in B, now we're looking at the common ion effect because there is an ion in common, right? Hydroxide is NaOH. It's also in manganese 2 hydroxide. So in scenario A, I'm looking at MnOH2 solid, adding that to a container of just H2O. And then in scenario B, I'm adding manganese 2 hydroxide solid to a container that contains 0.020 molar sodium and hydroxide. I know sodium I can ignore, it's not a common ion, it doesn't affect the pH, but hydroxide, that's going to be important. The molarity of NaOH is the same as the molarity of hydroxide because it's a 1-to-1 mole ratio. So, first of all, where do we expect the compound to be more soluble in pure water or in hydroxide? Well, based on Le Chatelier's principle and the common ion effect, we expect the compound to be more soluble in H2O than NaOH. That just means the molar solubility that we calculate should be larger. So let's give that a shot. So go ahead and pause it. So pause this video and then try part A, looking at your notes from practice exercise 8. When you're finished, go ahead and log back in and we will look at the next part together.